So now comes the next big step. Could this force of gravity, so we know it's responsible for the motion of the moon, but could the force of gravity be also responsible for the motion of the planets around the sun? Okay, now that's a big step to go from Earth, Moon to Sun, planets. All right. All right. So what Newton said is, I can prove that the force of gravity between the sun and the planets should also go like 1 over r squared, just like what I've shown for the moon, because I can start with Kepler's law. See here, now Kepler comes to help him, right? I can start with Kepler's law and work my math so that I can prove that the force of gravity between the sun and the planet goes like 1 over r squared. So here's how he did it. Now this involves a little bit of math. Don't try to take all the notes down very quick, because it's all in the appendix, okay? So just listen and digest it. So this inverse square law of gravitational attraction between the planets and the sun is a consequence, or this Kepler's law is really a consequence of the inverse square law of gravity. And here's the proof. So suppose the planet is moving in a circular orbit around the sun. So that's Copernicus, okay? Planet is moving in a circular orbit around the sun. We know the acceleration for this circular motion is produced by a force between the sun and the planet, which is the force of gravity. And the force is directed to the center of the circle, which is the sun. So that's all Copernicus. So there's your picture. There's the Earth going around the sun, okay? And this is the force of gravity. And here's the distance between the sun and the Earth, okay? Earth is one of your planets. And by the way, remember Copernicus stumbled over this problem, that if the sun is the center, why doesn't the Earth fall into the sun, right? And the answer is it does, right? Because the Earth is being pulled by the sun, but instead of going this way, it's going around. It's the same story about my water going around over my head, okay? All right, so I'm going to take this bucket and fill it with water and turn it upside down over my head, okay? And I will not get wet. So I will defy gravity. I will let that water stay in the bucket. All right? Okay, so just to prove to that, I'm going to have this transparent jug here. I'm going to add the water here. Okay, so we'll actually study the physics behind what I'm going to do, okay? But basically, I'm going to do this. All right? So it was over my head for a second, for a brief instant of time, right? For a brief instant of time, it was right over my head, right? Yeah, follow that bucket and see that it's really upside down over my head, okay? Right? The water didn't fall out. I didn't let the water disappear either. The water's in there. The force of gravity is still acting on the water, but the water, instead of falling on my head, is making a circle around my head, okay? Same thing. All right. So that explained this problem that Copernicus had. He said, why is the Earth not falling into the sun? And the answer is the Earth is falling into the sun and the moon is falling into the Earth, but that gives you a circular motion instead of straight fall. All right, so we continue now the calculation. So we use Newton's second law of motion, F equals ma, and write down the force between the planet and the sun. F equals mass of the planet times v squared over r, which is the acceleration. Okay? Because remember, acceleration here is this v squared over r times the mass of the planet. The force of gravity that the sun exerts on the planet depends on the mass of the planet. That's what he figured out. The force of gravity that the Earth exerts on the apple depends on the mass of the apple. Okay? So it's the same story here. So you put that down. Okay? Next he says, let me figure out the speed. Well, the speed again is the distance traveled divided by the time taken, and then you square that. Okay, 2 pi r over t, and you square it. I'm not going to do numbers now. I'm going to do symbols. So v squared is 4 pi squared r squared over t squared. That's this value here. Divided by r is 1 over r. So when you take this r and divide it into this r, you get the force is m planet times this value here. And now, he said, let me take Kepler's law r cubed over t squared equals a constant and use this to eliminate t. Okay, which means you can put this law as t squared equals r cubed times a constant and shove it in here to get rid of t. Okay, so when you do that, okay, you get F equals m planet times 4 pi squared r, and instead of this t squared I got r cubed times k prime, right? And now look what happened. 4 pi squared mass of planet over r squared. The force between the sun and the planet goes like 1 over r squared. That's the consequence of Kepler's law. So Kepler's great revelation of r cubed over t squared is nothing other than the force of gravity changes as 1 over r squared. That's what it is. So this was Newton's next big accomplishment, which really said that he synthesized earthly motion, because everything is based on the understanding of circular motion. He synthesized this earthly motion with all the motion of the planets. Okay, this is a grand synthesis. And so if I pause here before I go to his next insight and give you some kind of artistic relief, I'm sorry, first of all I'm going to give you a summary. The force which the sun exerts on the planet is the same force of gravity which makes the apple fall to the ground, makes the moon go around the earth, makes the planets go around the sun. And this is nicely captured by Byron in his poem. I think this poem is in the book. It says, when Newton, sitting in that garden, saw an apple fall, he found in that slight startle from his contemplation a mode of proving that the earth turned round the sun in a most natural world called gravitation. And this is the sole mortal who could grapple since Adam with the fall or with an apple. All right, so come back to the math part a little bit. What have we shown so far? Okay, we are after showing how he came up with this grand law, and we've shown that if you had a body here of mass m2 acting on m1, then the force of gravity will be proportional to the mass of m1, okay, and 1 over r squared. That's all we've shown. We still have to show the rest of it and this constant g. Okay. So now we come to the next great insight of Newton, and this is this third law. Okay, and this law is what is called the law of mutual attraction. Okay, so we discussed this a little bit when we talked about sailing. Okay, so just to review again, the first law is the principle of Galileo. Okay, and the second law of motion is equal to F ma, and now we come to this third law, which is actually the third pillar of mechanics, and I'm going to demonstrate this law for you once again on this chariot here. So here I have two bodies that are interacting with each other. Yeah, I'm going to pull these two bodies together. I'm going to let them interact, okay? And after they interact, I want you to observe how the motion is of each body. They're about the same, okay? They're symmetrical bodies, okay? So now here they go, they're interacting, they're fighting with each other, and I let them go, all right? Once again, I let them go. You know why they're repelling, right? There's a magnet in between, all right? The North Pole, and they're repelling each other. But notice that if the bodies are exactly the same and the same mass, that the force that body 1 exerts on body 2 is opposite in sign to the force that body 2 exerts on body 1, because this guy goes this way and this guy goes that way, right? So this force is acting this way and this guy's force is acting that way, right? So opposite each other, and they're equal because the acceleration is equal. So the acceleration is equal and opposite. This is Newton's law of action and reaction, okay? Acceleration is equal and opposite. All right, now I'm going to do a little bit more dramatic demonstration of this. And this demonstration will also be the demonstration of how we use rockets to go to the moon, right? So we take the rocket and then we light a fire underneath it, and all the fire goes out one way and the rocket goes up, right? So here I'm going to be the astronaut. You might want to go up one level. You'll be okay. Actually, instead of going up, could you stand by this chair and block me from going into orbit? I'm not going to go that fast, but sort of catch me, right? Okay. All right, so so you see what this is, right? This is a jet. All right, okay. And I'm going to go that. Ready? Thank you. All right. So there's enough gas here that a couple more people can try it after class, okay? But just make sure somebody catches you. Now, what was being expelled was carbon dioxide, okay? And so the mass of carbon dioxide was going that way, and because of the mass going this way was exerting a force on me equal and opposite going this way, okay? So there's your Newton's third law of action versus reaction, okay? Okay, so what Newton realized is that two bodies always interact with each other, and that's why we get forces, okay? And that whenever there is that interaction between two bodies, A and B, the force exerted by body A on body B is equal and opposite to the force exerted by body B on body A. Are you trying the same thing up there? Okay. He comes to the conclusion that the Earth attracts the apple should also attract the Earth. Similarly, if the Earth attracts the moon should also attract the Earth. And we'll show you later on that you see that all the time when you go to the beach. The tides come in, that's the moon attracting the Earth. And we'll show you that. In fact, Newton used that to figure out the mass of the moon. And the Earth should attract the sun. So then the question is, if the apple attracts the Earth, why doesn't the Earth just fall into the apple? Maybe it is. Okay, and the answer to that question is the following demonstration. So here's my card again, interacting with this other card. Okay, we still have the magnet interaction. But now, let me increase the mass. Let me pretend this is Earth and this is apple. And since the Earth is much, much more massive than the apple, let me increase this mass and now do the same interaction between these two. And you'll see that the acceleration of the lighter body is much, much bigger than the acceleration of the Earth. So yes, the apple pulls the Earth, but the acceleration of the Earth is insignificant compared to the acceleration of the apple, right? So you can figure out what the acceleration of the Earth is. Okay, so now Newton comes to the conclusion then that in order to have symmetry in the world, to symmetry in nature, that you should have not only these arrows, but there's more, that the sun attracts the force of the gravity, but the planets attract the sun with the same force in the opposite direction. And so this picture should be corrected by having this picture of mutual attraction between these objects, okay? All right. Now, if the Earth attracts, now here comes the puzzle. If the Earth attracts the apple with a certain force, and the apple attracts the Earth with the same force, why does the Earth not accelerate towards the apple? Well, I already gave you the answer to that. Because of the mass of the Earth is much, much larger than the mass of the apple, and I did the demonstration, okay? And I already talked about the tides. All right. Well, now, based on this, Newton comes up with a brand new consequence. And now let me write down some equations to show you the wonderful consequence. So let's take the Earth and the apple, and let's write down that the force of gravity on the apple is proportional to the mass of the apple. He figured that out in the garden, right? Okay. Now, force of gravity on Earth from the sun, right, is proportional then to the mass of the Earth. Let's say we consider these two. So the force of gravity that the sun has on Earth is proportional to the mass of the Earth, similar to this picture here. Now, let's use this law of action and reaction to say that the force of gravity that the Earth exerts on the sun must then be proportional to the mass of the sun. So I write that down. And symmetry commands that these two forces should be the same in magnitude and opposite in sign, right? But the mass of the Earth is so much smaller than the mass of the sun. So how can these two forces be equal? This is a big puzzle that Newton faced for a while, and he solved it very easily by sleight of hand. He said, this law is incomplete. The force of gravity on Earth from the sun is not only proportional to the mass of the Earth, but it's also proportional to the mass of the sun. So he multiplied the two together. So he said, now you've got the fact that if I now write sun on Earth, then I still get mass times sun mass times. So now these two terms can be equal, and the sign, of course, can be opposite. And then put it all together, okay? The force of gravity is proportional to mass of planet times mass of sun divided by 1 over r sun planet squared. This is true for the Earth-Moon system. It's true for the Earth-Apple system. And now I can generalize it. Comes the next big step. I'm going to generalize this to any two masses. Okay, there's nothing special about the planetary system. Any two masses, okay? You and me, any two masses, right? Generalize. The force of gravity between us remains given by this law, product of the two masses divided by r squared times a constant. That's the law of gravity. See? All these steps he took to get to this grand point.